Hello friends, how are you all today? Have you ever wondered what operating system is and how it is going to work? It's coming up right now. I'm Prashant, a technical trainer and freelancer from Dharani Academy of Technical Education, Bengaluru. Let's start with the concepts of operating systems.
Okay, now we were looking at the specific format using which we can use a page table so that we can access, right, and we can differentiate the page files that are loaded into the main memory of computer and that have not been loaded into the main memory of the computer, and it indicates that it is present in the hard disk. So uh, here from this diagram it should be very clear that uh, if a page is invalid, right, that will have no effect if the process never attempts to access that particular page, right. Let's say there is an invalid page and you are not going to try to access that at all. The program that you are running is never going to try to access that page which is marked as I. If that is the case, then there is no problem, right. So if uh, the guess is correct and the page in only those pages which are actually needed have been loaded, right, the process will run exactly as, right, as it will run when you load the complete set of pages to the main menu, right. There should, so whichever page is needed should be guessed properly and they should be loaded into the memory. This is the idea. Okay, but before that let's write those points uh, first. Okay, now the first point here is I'm trying to load only which is required. So that is marking a given page as invalid. If you do so, uh, will have no effects if whichever process that is running now, if I can write the process it never attempts to access that page. Okay, if it does not try to accept that page, then no problem, right. This is the first point. Now how do you support this? This can be supported provided the guess, there will be a guess, right. Previously we discussed that there is a guessing technique. So you will guess which are the required pages that needs to be loaded corresponding to this specific process. So there are several types of processes. We will be looking at the details of variety of processes later, right? So maybe it is related to IO handling, input output related to that. It can be a functionality. It can be a GUI, graphical interface, right, etc. Depending on each of the requirement of a process, there will be types using which you can try to access several sets of pages specific to the function. So the one which is going to perform this guess will know, okay, if this function is to build a GUI and show the user different concepts related to the user interface, then these are the required pages, right. According to that it will make a guess and it will load. So if this guess is correct, right, and the page, everything is loaded according to that requirement. Process will run exactly, right? Exactly, it is going to run how it will run if you load the complete program. But now we are not doing that. We are doing only page by page loading, whichever is required. Okay, so if the guess is correct, if the guess is correct, and only the, okay, I can write only those pages that are actually and only those pages that are actually required have been loaded. That means you guessed it correct. Then what happens? Then the process will run. Then the process will run exactly as though we had brought in all pages. So now it means it doesn't matter whether you load complete page, all the pages required, all the pages available, or only the pages which are required. It's going to run in a very uh, compatible fashion. Okay. While the process executes and accesses the page that are memory resident, execution proceeds in a very normal fashion. So we bring in the term now. The term is called as memory resident. Okay. So the processes which executes access the pages which are present in the memory, we call it as a memory resident pages. Okay. So this means we access what is called as memory resident pages. These pages which are actually present in the memory and they are required by a process, we call it as a memory resident pages. So you access memory resident page, it means the process is going to run in a very normal fashion. Okay, now let's go ahead. But what's going to happen? Now we'll look at the other side. That is, what is going to happen if a process tries to access a page that was not brought into the memory? It's not present in the memory. Okay, right? Which is not present in the memory. How do you come to know? You look at the table. Page table will give you a very clear idea, saying that if it is V, you can access that. That is memory resident. But if you try to access any file which is marked as I, that means it is invalid. Okay. Uh, this is the next point when we try to explain the concept of paging. Here we try to access a process. A process is going to try to access a page that is not in memory. So if a process tries to access a page that that was not into the memory, right? That means it is invalid into the memory, right? Comma, right? Uh, trying to read invalid page. I can write this in bracket. It's understood, right? There is a specific event that is happening. That event is called as can call causing causing uh, page trap. So the particular situation is called as page fault trap. Okay, the paging hardware, already we discussed that there is a hardware which supports this. So which hardware? That's the hardware which allows you to mark V or I for a given page, right? That's a hardware. We are looking for a hardware because you are representing in the form of a bits. Binary data is stored in the memory. It indicates that it is a hardware. So that's why we mentioned that we need a specific hardware wherein you are allowed to mark ones or zeros, right? Here we showed it as a V or I, but normally you are going to do that using zeros or ones. It's a so now the paging hardware in the translation process of the address through a page table will identify that the bit is set as invalid, right? So it doesn't know what to do. So that's why we are going to call it as the trap of the operating system. Operating system will fall into a trap over there, right? Okay, we'll write that point now. What happens to the hardware? So the paging hardware, right? In okay, in the process of translation or the translating the address through uh, the page table, while it is using the page table, it will look for whether that particular page is valid or not. Okay, so through the page table, will notice that it will notice that the invalid bit is set. It is set now. It is set to a invalid. So means what? It causing a trap, causing a trap to the OS operating system. So what is the result of this trap? The trap will result in operating system's failure to bring the desired page into the memory, because we know that operating system itself has a built-in feature of virtual memory concepts. But when the virtual memory, which was a result of, or which was a specific feature of a OS, right? Now OS is not going to handle that because it missed something. So this means it results in the OS failure. We say that, right? OS failure happens as a result of the trap. Okay. So this trap results in OS failure to bring the desired page. Okay, now is there any solution to this? Now because see, we whenever we face a problem, right, we need to think how to resolve that, right? Is there any idea using which I can overcome this issue? Okay, and the answer is yes, we can do that. All right, so the next topic that comes here is called as, right, procedure to handle traps. Any such situation that arises, right, in an OS can be handled by using what is called as a standard procedure. Every OS will follow the same thing. Okay, right, let's try to write that. Okay, somewhere here, right, I have a memory, and the memory is asking to load something. All right, so we call that as a, maybe it can be a function, right, which is written in the area that is corresponding to storing the code instruction, and the instruction says that load something, which is, maybe we call it as load m. I mean, m can be a variable, m can be any function like that. So as soon as this is located, right, computer is going to check, right, whether it is present in a particular page file, right. So we have paging that is happening over here. So page file, so this is the page table. All right, so load m will be directly referred to a page table. Okay. Now whenever it is not present, we have the result, which is nothing but a trap. Trap is a specific situation that is uh, related to the OS. Okay, we refer now, this is the operating system, right. This particular situation, when the table is not finding the required data, will result in the next situation that is actually called as a trap. So this is, okay, let me give some numbering here. This is one, stage number one, which is called the reference. Okay, so I'll write here, this is reference, that is number one. So number two, second case, is a trap. It is not present. So the solution starts now onwards. That is, will refer it to the disk now. This will be referred to the disk. Okay, the situation is directly referred to the disk, indicating that this is what has happened. So now you look into the solution. So this will be directly referred to the disk. Okay, and that stage is step number 3, and step number 3 is called as, what's the name, its page is on what is called as a back. There will be a backup always, so the plan is to go for a backup. Let's write that. So let's say this is the particular cell corresponding to the required data, so this will be directly referred to this. Okay, so I'll write this is step number 3. We'll say the page on, it's called as a backing store. It will be stored somewhere as a backup, we call it. Now this means what, if you write a disk is nothing but the physical memory, correct. So we'll show the physical memory now. Okay, so I'll write the physical memory, and let's say you are trying to bring that particular frame. So the technical word for uh, the paging file, the particular data which is required, is a frame. Okay, so this is the physical memory. So what we do, we bring this into a specific location in the physical memory. So step number 4, we call it as you are trying to bring in missing page. So here we refer that page which is coming into the physical memory, which will be called as a free, FREE. This is a free frame, indicating that you can put it anywhere. All right. So then this is, so it was actually searching at this location, correct? You see that it was searching here and it was missing from this location. It's not present over there. So what you do, this frame now needs to be, right, replaced at that location. This will be put up over there. Okay, so this is number 5. Step number 5, right? This is called as the reset page table. So after this, now you see that that instruction is now available in the page table. Now you can put this back to the load m. So that is step number 6, right? Step number 6 is restart that particular instruction. So this is it's a process. Like, initially you will ask for something, it is not available in the page file, you generate a trap specific situation, right? That actually we try to terminate the particular process, because that process, whatever data is required for that process, is not available. So as soon as you find that it is not available, right, we have the termination will occur immediately, right? Process is valid means it will proceed further. If it is not valid, indicating that right now that required resource is not available, immediately it will terminate. Okay, I'll write all the steps, but just let's try to recall. Right, then what happens, you have a backup store that is present. You try to find out what is called as a free frame, right? So why it is called as free frame? Because it is not present on the list, right? So that's the step number 3, to find out that. Then bring it, right? There will be a read write operation related to that, so that will bring the particular desired page to a newly allocated frame called free frame. Then disk will read this, perform the read operation. Once it is complete, we modify the internal table, that is a page table, and we'll indicate that okay, at this location the newly arrived frame has been kept. So that will be passed on to the original instruction, maybe the load and part, right, which will be restarted, right? So now since it is present over there, you can see that it is not going to generate a trap once again. All right, so these are the steps. So step number 1, I'll write with the same numbers. So check the internal table for a specific process to determine whether the reference was valid or invalid, right? Because if it is valid, if it is marked as V, it means yes, the data reference to that data is directly present in your memory, otherwise it is not. Okay, so now let us assume that it is invalid. Okay, so in step number 2, if the reference was invalid, okay, then what happens, right? The process gets terminated. It gets terminated. So I know that if it was valid, right, if it is valid, it will run. Okay, so this situation, as referred in the diagram, it says that it is a track. Okay, in bracket you can simply call it as a track, right? So step number 3 is locate a backup and find out, right, where is that frame. We call it as a free frame. Okay, uh, normally every required frames copy will be kept it in a separate something like maybe a folder. We call it as a free frame list. Okay, from that you are supposed to find out a free frame. That is step number 3. So find out the free frame, right, by, I can say, by collecting one from the free frame list on the disk. We know that it's present on the disk, right? That is step number 3. You just have to identify that, okay, where is the backup for this particular page, right? Once you find that out, the step number 4 is, right, now the processor has to perform the read operation of a disk because it is present on the disk. So schedule, there will be a scheduler, right? OS has a controller part which normally schedules all the processes, right? We know that processes get scheduled as per the requirements, right? There will be some queue. If a process is terminated, you know that it can come back, it can sit in a queue and it can come back, etc. We have a standard procedure over there, right? Now under the current scenario, there will be, right, a schedule for a disk operation to read the desired page into the newly allocated frame, right? We said that it's a free frame, right? It has to be, you have to read it from the memory. All right, so then we can say that I can write a disk operation gets scheduled, right? Why? To read, to read the desired page. That particular page has to be read into the newly allocated frame. Okay, so that's step number 4. You are bringing in the missing page to the free frame in the physical memory, right? And the step number 5 is nothing but, if the read operation is complete, it will modify, or it will perform a reset of the table. We call it as internal table will be modified and kept with the process, and the page table will indicate that, okay, the page is present in the memory now. So the invalid tag will be replaced with the valid tag. That's the indication. Anyway, you don't have to specify that, it's understood. So the step number 5 is, once the read operation is complete, right? The internal table or the page table, right? The page table kept with the process gets modified. It gets modified, okay? And the table or the same, the page table will now indicate that the page which was missing, okay, is now inside the memory. Okay, I can write in the memory of the computer, right, where it can directly get executed. So it once this is done, now the instruction which resulted in a trap, right, will be restarted. So that's the last step, step number 6, right? Restart the instruction that was interrupted due to the trap situation. So the process can now access the page, right, and it's already present in the memory, so there is no trap resulting now. Okay, so we can restart executing a process, right? Normally that's the standard way of OS says that. This was an older technique because our textbooks are pretty old. In that, when they wrote these textbooks, the original OS was supporting the page up to 110. Okay, 110 pages could be loaded directly into the memory. But anyway, that has been changed. Like the current value, I'm not aware of. But anything maybe more than 1,000 or something, possibly. Okay, so when operating system sets the instruction pointer to the first instruction of the process, right? Normally that will be a non-memory resident page. It will not be present in the memory, right? So whenever OS points to the first instruction, definitely the first instruction is not present because only when you read it, you will come to know. Okay, so what happens? The process immediately faults for this page. This page is not present. It will say that it is not present. So the instruction queues will start after that. Okay, not with the first. Whenever you click on an icon, right, the program related to running that particular icon is not present in the memory. Immediately the trap will be generated internally. It will follow these procedures and load this, but when this is happening, you will you will make sure that the OS is going to read the next instructions in the instruction queue. So instruction queue is like you are trying to look what is going to come next. So your instruction pointer will point to that now because the current instruction is under process and you already escalated saying that there is a trap. So while your system is reading the first instruction, second instruction will come into the instruction pointer, and then things will speed up, saying that okay, this is the second instruction. If it is not present while the first instruction is being executed, you do the required process for the second instruction, third, fourth, and so on. Right? Normally, at least some tens of instructions will be present in the queue, so that right whenever computer is executing something, the future instructions will be loaded and kept it ready in the virtual system, virtual memory. All right. Okay. So let's write that as a next point under this case. So when OS sets the instruction to the first particular instruction, okay, when the OS sets the IP stands for instruction pointer, uh, to the first instruction of any process, I know that that particular first instruction, right, is basically non-memory resident, right? Uh, I know that if it is memory resident, it will run normally. But since this is non-memory resident page, right, the process results on trap. Right. Now we know that standard procedure will be followed, and as soon as the page is brought into the memory, process will continue to execute, right? Until every page that is required in the to run the whole process, until you bring every pages onto this, there will be a halt, right? Maybe that process will be right. If there are no other processes waiting in the queue, right, this process will be halted, and when pages will come, it will continue. Okay, so after the page is brought into the memory, now I know what is the standard procedure. 6 steps are there. Everything will be followed, and you bring that into the memory, right? Process continues. Process will continue. Okay, so now there will be uh, no situation of a trap, no error. Okay, so this particular scheme, right, where you try to load in all the required pages so that you run a process without any faults, right, we will call this technique is it's called as a pure demand paging. Okay, so this particular technique is referred to as the pure demand paging technique. So pure demand refers to you are not going to bring any page into the memory until and unless it is really required. Don't load anything which is not required. Okay, so that's about this. Now we have we talked about what is called as the hardware support. So when we say that we require a hardware to support the demand paging, right? So it's the paging hardware and the swapping. Both concepts are very same. So in the previous chapter, we have the concept related to the swap. Okay, the swap requires some memory. The similar memory is actually required even in this paging case. Okay, so let's write that point here. So I'll give the names of the hardware as well. The hardware to support demand paging. So we have two things. The first one is even the hardware is referred by the same name, that is the page table. I know that the page table is a memory, right? This contains memory cells. So it's a table, right? But it has to have a bitwise support to mark an entry as valid or invalid, right? Special value. So again, when you read or write some data, these particular bits should not be altered. There has to be some protection for them. So that's why it is a specific type of hardware with some special features. All right, so we call it as table, but it's a hardware. Okay, so this table has the ability it has the ability to mark an entry to mark an entry invalid by using valid invalid bits. Okay, so with I'll just write with some protection. Okay, with the protection. Whenever you have some protection, you can safeguard those bits. So easily the bits should not get altered. So that's why it's said to be protection. So that's the first hardware required. The second hardware that is most necessary for demand paging is called as the secondary memory. This is also equally important. So this memory holds those pages which are not present in the right main memory. So that's why we call it as a secondary memory, right? Normally this would be the hard disk that is present in each and every computer. Okay, so in the previous chapter we call this type of secondary memory as a swap device. Okay, that is a section of the disk used for this particular space is called as a swap space. So when you install an operating system, you will see that some part of your memory will be occupied, and if you open the disk space, it will show that not available for the user. What do you mean by not available for user? OS will declare that part of your main memory as a swap space. Okay, so there is a huge concept related to the swap space, right, which will come in maybe in the upcoming chapters. As of now, let's just remember the word swap space. Okay, right. So what is secondary memory? This memory is used to, or it holds the or holds those pages that are not present in the main memory. Okay, so which means, right, you can call it as a right not present in the main memory. Okay, if I write a bracket, it means the main memory is the hard disk. Okay, let's not write that. So let me write this. The main memory. Okay, so I'll write as a next sentence itself. Usually the hard disk is used for this purpose. Okay, we use the hard disk. All right, now what happens, this device, but it's not the whole hard disk. You are not going to use the whole hard disk. You are going to use the specific part of the hard disk, and that space which is used for this particular purpose is referred to as the swap space. Okay, so the section of the hard disk used here is called as the swap space. So how the OS decides the swap space, right, and how this could be implemented, etc., will be coming up as a later topics. Okay, now uh, okay, the next concept that we'll be discussing is how you are going to restart any instruction after you identify that there was a page fault. Okay, so we save the particular state of the instruction, right, whenever there is an interruption. Page fault occurs means computer knows that, OS will identify that there is a trap and we cannot go further. So when we say that we are going to terminate the process, it is expected that you save the state of the particular process. What do you mean by state? What are the current values of the register? What happens with the condition, right? Conditional, what you call conditional coding, and the instruction counter, the pointer which points to the next instruction, because you have to go, you have to look at the particular uh, data and come back and execute. Okay, meanwhile you can handle the others, right, but definitely this is the case. So you need the current state of this particular instruction to be saved. So that's the first point, uh, how to handle this trap after this six steps have been taken place. How do you restart? So in order to restart, I need the current status, which is that particular instruction that actually caused a fault, right? So it is because you, when you restart, you should restart the exact process, right, which was the particular instruction that halted. It should be continuing from where you stopped, correct? So that's why this is important. So what you are supposed to do now, let's write that same point which we discussed. The demand paging needs to be able to restart any instruction after the page fault, right? So how can you do that, right? This can be achieved by saving the state of that interrupted process when the page fault occurs. So uh, save the state of the process. What do you mean by saving the state of the process? In bracket I'll write, you will save the register content. You will also conditional codes. in the sense it can be the status flag registers. Okay, and also you save the instruction instruction actually pointer, but textbook says a counter. I can write the same thing. Okay, instruction counter, right? So to save, so we are going to save the state of that particular process as soon as the page fault occurs. We'll save that, right? Then why do you do this? Because we can restart the process in the exactly the same place and same state, right, except the condition that the desired page is now available in the memory and it can be accessed. So save the state of the process including all this, so that we can restart the process. In what sense? In exactly same place, because process have so many lines of codes. At this particular point there was a trap, so you find that, you bring it back and you continue from there. You don't have to go back and do it from the beginning. That's why the word says that exactly same place and the state, because once you come back, right, you can load it, same space comma uh, same state, right? I do it at the exact same place and same state, except the desired page is now available in memory. It's available and you can access that. Okay, and it is accessible, right? Using all this idea, right, you in order to restart you need to save. So you save it, follow the 6 steps we discussed and come back and continue, right? So overall idea is that we cannot avoid the page faults by default. There can be a page fault occurring. Normally it occurs whenever you begin something which is new. Okay, because when you run something new, computer doesn't know where is it located. It will definitely throw you in a trap, right? So then you need to have a solution to look at how to overcome that. How do you load the data which is present, which is required for the process and present in the disk, not in the main memory, right? You can follow that step, right? And if you save, it is easier to continue from where you stopped, right? Otherwise what is required, you have to start from the very beginning, right? And it will definitely waste a lot of time uh, of the computer. Okay,
That's all for today. Let's resume the concepts in the upcoming classes. If you have any doubts related to the topics we discussed, please feel free to contact me anytime. Thanks for watching. Have a nice day. Goodbye.